Thank you, John. Well, I think everybody's going to have a fun time this evening. I know I am, because it's going to be an absolutely exciting presentation. Exciting from the standpoint of seeing people excel at what they do. Exciting from the standpoint of seeing people take a scientific question for which there were no easy answers, so this was not like a textbook experiment, no easy answers, and try to figure out how do we design some experiments to learn more about this phenomenon. So I'm not going to steal their thunder by telling you all about their experiments, but I did want to give you a little bit of background tonight on what radio astronomy is, for those of you who perhaps are optical astronomers and don't have a strong background in radio astronomy. We're going to talk a little bit about what it was, tell you what we're doing with radio astronomy here at Little Thompson, and then introduce Scott Kindt and students from Berthoud High School to talk about some truly exciting work they've done this summer. Well, first of all, what is radio astronomy? Those of you who have studied this will not be news, but for a lot of optical astronomers, it really is. The whole question of what is radio astronomy sometimes sounds mysterious, but it really isn't. So we're going to talk about these things here tonight. And first of all, to give you a little background in radio astronomy, it's not that much different from looking through an optical telescope in terms of the physics involved. We're looking at photons coming from some other place, just like you would do with an optical instrument. But we have to use some radio and electronics equipment because the wavelength is so different. But a radio telescope has some limitations, but some huge advantages. It's very much like a 1-pixel camera that has an extremely fast shutter, maybe on the order of thousands or tens of thousands of times per second. It can take an exposure, but only 1 pixel at a time. And then something that many people don't think about, we can gain information about other things by direct emissions coming to us from that other object, or by radio waves that are reflected off something, like meteors, for example, very similar to the process of radar. Now, my guess is everybody in this room has heard signals from outer space. If you remember the old-time television with rabbit ears and a lot of snow on the screen, well, a goodly percentage of that snow is actually noise coming from space. And when you turn on the car radio, AM channels, and you're in between stations and you hear crackling and so on, well, a little bit of that crackling may be coming from your engine or the tractor trailer rig next to you, but some of it is probably coming from space. So what we do with radio telescopes is we concentrate on those signals coming from the sky, try to analyze them and get some meaning out of them. Give you an idea of what you can do with radio astronomy. This is a beautiful optical image, and we don't have to play the audios here. Beautiful optical image of Jupiter, but when we look at Jupiter in radio waves, we see something else. We're not seeing nearly the definition, the sharpness that we did with the optical image, but we see other things. And here we're seeing some radio emissions that are coming from the magnetic fields around Jupiter. So we can learn some things about Jupiter with radio that we couldn't see optically. Venus is the same. Now on the left is a composite image from radio and radar. Radar is a type of radio. And on the right is about the best optical image we could ever obtain from the Earth of Venus. So this is a fairly good example of how radio and radar technologies can give us more understanding of something than we can pick up just with even the best optical instruments. Now, radio astronomy is a fairly new field of science. That's a good thing for those of us who are trying to make original discoveries, because it's a wide open field in a lot of areas. To give you some background on how it came about as a field of science, it actually started with this gentleman, an engineer working for Bell Laboratories, trying to find out why certain telephone circuits that used radio were being interfered with. In fact, so severely that they would lose circuits very frequently between New York and London. So in 1932, Bell Labs had one of their engineers look into it. He built this beautiful contraption over here, which is a radio antenna hooked to a receiver, and he found that the noise was coming from space, and specifically from the constellation Sagittarius. Most curious, because later on in the study of this, we've discovered that was the center of our galaxy, and probably a black hole was causing an immense amount of radio signal to be emitted from there. But nobody paid much attention to his findings. He was a radio engineer, not an astrophysicist. So he had a paper published on his findings, but it was published in telecommunications journals, not any physics journal. So pretty much no one paid attention to this outside the telephone and radio world until a few years later, a ham radio operator in Ohio named Grote Reber came across that paper and decided with his wife's permission to build this in his backyard. So he built a tremendous radio receiving system and actually did the first radio map of the sky. The first done in the world was done by just a volunteer with stuff he had put together in his backyard. Very knowledgeable volunteer, but again, not a lot of people paid attention to his findings because he's not an astrophysicist. During World War II, two people who were renowned physicists, or who became well-known, but at the time they were doing their work in secret in farmlands in the Netherlands. A professor and his graduate student did some theoretical work on what radio emissions might come from different elements out in space. They predicted, for instance, that hydrogen would produce a radio signal, a powerful radio signal, on the 21 centimeter wavelength band. And that's just about right in the middle of where cell phones operate these days. But they had no radio equipment available to them to do any experiments. All their work was theoretical. And it wasn't until after World War II that folks started marrying the work done by Grote Reber, which was the building of a dish, with the theoretical work done by these two, and the science of radio astronomy was developed. So that's within the lifetime of some people in this room. It certainly was within the lifetime of my parents, and probably for everybody in this room, you have a relative who was around back in 1932 when Mr. Jansky, a whole lot like Galileo, turned his instrument to the sky and saw some things and started documenting them. So everything that radio astronomy has accomplished has occurred since 1932. Here at LTO, we've tried to put together a radio astronomy program that's approachable, workable, and practical. So again, you see our volunteers up here. Everything here is done by volunteers. We didn't have to pay a penny for any of this stuff because people put their time and effort and money and brain power into it. But just about a year and a half ago, we turned on our radio telescope for the first time in public, and Sven Kindt, who is sitting right there, is the fellow over there who actually turned on the power switch for us that night. So we had a great celebration that night, and much of the things that you'll be hearing about later on tonight have come out of trying to find practical ways to use the equipment that we have. Most of the equipment's in the room back behind us. The antennas are just immediately to the south of this building. One of the most interesting projects to come out of this is what you'll be hearing about tonight from the students from Berthoud High School, who asked some very interesting questions and designed some experiments to try to answer them. So this is the team. They'll be introduced to you in just a few minutes. One person is missing from the picture. She took the photograph. And they will probably explain to you a little bit more about that. But beginning last April and through the summer, this team has really been conscientious workers, good scientists, who really put a lot of time and effort into understanding the science behind what they were going to experiment with. And I think you'll be very pleased to hear their reports. These were the people who worked with them. And if I could just go ahead and put Dr. Terry Bullitt and David Eckert on the spot and ask you to stand up. David and Terry, working with Scott Kindt from the high school, just dedicated their entire summer, literally, to this project, working with the students to refine the science and make sure that the work that was done is truly creditable in terms of being valid. We also had help from the National Radio Astronomy Observatory in Green Bank, West Virginia. Dr. Catherine Williamson from there gave us a tremendous access to resources, not the least of which was a wonderful radio telescope located in West Virginia, which we could access remotely right from here. A 20-foot dish. So that's a nice sized radio telescope. So with that, I would like to introduce Scott Kindt from Berthoud High School. He was the coordinator for this project. I'll let him explain a little bit more in detail about what's involved in the STEM program and how the students proceeded with their projects. So Scott?
All right, thank you, Jay. All right, so my name is Scott Kindt. I teach science here at Berthoud High School. And just a little bit of background, didn't mean to hit that. A little bit of background on what the project is. I saw Crystal Domenico, where are you? Yeah, could you stand up for a second? Okay, Crystal Domenico, she's our STEM coordinator at Berthoud High School. And that's basically the premises of how it got started is juniors that are in the STEM program at Berthoud High School get to pick a research project to be involved with. So I was, being a physics teacher, radio astronomy sounds pretty cool, but I'm no expert on it. I thought, what a neat thing to start. I didn't know what I was getting into, okay? But so that's how these students ended up in the program as part of their STEM research internship that they do in the summer of their junior into their senior year. So that's how it got started. As a professional educator, science teacher, the one thing I will say is this was an amazing project. As a science teacher, we're stuck in this box of we do these 90-minute labs, we know what the outcome is, and it's kind of like, that's not really science. But doing a project like this was real science. So I was thrilled to be part of this, where there were questions that came up where we didn't know the answer. And it was really neat seeing these fine young ladies and gentlemen, how they problem solved it, how they got through it, how they were thinking like scientists and engineers, and how they solved those problems. But none of this could have been done without Terry, David, and Jay. They were the real heroes of the time they spent, the expertise they did week after week. We would meet with the students throughout the summer, even into the school year, following through with them, coming in during lunch. Couldn't have done it without them. They were an amazing group. I would love to work with them again, and I have grown so much as a teacher, so I can't thank them enough for what they've done. But enough about this. Let's talk about these gentlemen here. So Xander, Colin, Zach, JT, and Sierra, they basically, when they got into the project, they didn't know what they wanted to do, just something with radio astronomy. And as we got into the project, we started doing different things, and it kind of unfolded, and it was kind of neat to see how they got into something. First, we made a loop antenna to do Jupiter, but it didn't quite work, and then something else evolved into that, and then before you know it, they had 2 individual projects, and I'm going to kind of turn it over to them to let them explain what those projects are, okay? So, who wants to go first? Oh, there you go.
I'll take this.
Okay.
How does this work? So I'm JT. I'm going to scoot over a little more. So like Kent said, we started this our junior year, and we came in, and speaking for myself, I really didn't know anything about radio astronomy. I was into science and hands-on stuff, but the way Mr. Kindt described this, it was a really cool opportunity to get involved and, actually study something that isn't really known. So we started it with our STEM program, and we got in this, and then we, like Ken said, we started with one antenna and went to the next, and we got to study meteorites, using the radio telescope to identify them and locate them and see how many there are.
So, I'm Colin Miller, by the way. What we did basically is we detected meteorites. How we did this is through a simple technique that astronomers constantly use, what it seems like radio astronomers constantly use. We took our radio antenna that was here, and we found a transmitter, aka a giant satellite dish that was either putting out radio or TV station, something like that, over the horizon, in our case, Mexico. What we then did is that as that transmitter over on the left side, if you look at it, was putting out its radiation, it shoots it off, and it goes off tangent of the Earth into the atmosphere. So we don't hear it from here, but it is still being produced. This laser pointer. There we go. Right there, it goes off tangent right there. Now, as a meteor goes through, it creates an ion trail of positive negative charges in the atmosphere, right here, and the radio frequency bounces off that trail and comes down to us. Now, us not being able to normally hear Mexico television and stuff like that, we were able to then tune into that frequency and discover like a little beep or a little bump within that frequency appearing down here in Colorado at our receiver point. And that's basically the general science behind what we did. We're just taking a giant radio telescope transmitter in Mexico, launching up, reflecting off a meteor that comes through the atmosphere, and then boom, we're getting it here. So
Is there any questions about that?
So the signal that they were transmitting is just the regular TV?
yeah, actually, a little fun story about that.
Yeah, but yes,
it is a regular
radio.
TV station. And as we were here one day, we were trying to actually figure out what it was, and a sporadic E event was occurring, which is a time where the atmosphere kind of condenses, and a lot of these radio wave signals that you see over here just end up bouncing off the atmosphere naturally. So we tuned up the frequency here and turned it into an audio speaker, and we started hearing a Mexican car commercial.
Yeah.
So
That was
little
weird.
fun things you could do. It was kind of weird, but kind of funny at the same time. We're like, where is this? Is it Canada, Mexico? Then all of a sudden, it sounds like a soccer commercial, honestly. They start speaking really fast Spanish. You're like, oh, hey. There we go. So then, the start of our project. Want to go over this here too?
So this was the loop antenna we used for the Jupiter project, and this is really, we started this last year in our junior year. You can do it.
Oh, yeah.
I'd like to say this project went smooth, and everything hit right where we need to, but it really didn't. It was up and down and all over. So we decided to do this loop antenna, and it was going to be a cool project. We're going to get it going, and it went downhill fast. Scott can testify for that. But it put us on a new path that got us even a better project than that was going to be. So we made this antenna, and we had to do some engineering to make it, and like this big plastic block we had to make, and we kind of just had to put it aside and move on. So next slide.
I have too many clickers.
Here, give me these.
There we go.
You do that.
Okay, well, back to this slide initially. What we did end up using, however, was our dipole antenna. That right there is an antenna that looks like this. So it's about half a wavelength, so you get the optimal usage out of your antenna, basically. So it's a half a wavelength long. For us, that was roughly about 25 meters or something like that. It was a large telescope. It's probably as long as this room. So what we then do is we hang it up anywhere. We hung it up on top of the school. We ended up hanging out at a farm later, and we were able to detect the signal coming back from any of that. We would have the telescope here, but unfortunately it is sitting at a duffel bag somewhere in Loveland. So we also then used our Yaesu transceiver to convert the signal that we were receiving into a file that your computer and a program can read. And that's basically, if you look over there, laser pointer, right there, that right there is basically how we set it up. The wire was going across from a tree to a house in our case, and going back down to our transceiver into a computer so we can read the data.
In that first photo of our group, it's hard to see, but the antenna is actually running parallel to us.
Right there.
We're standing right, yeah.
It's cutting off Zach's
Yeah,
head.
it's this right there.
Yep,
So
there you go.
we actually set the phone in a tree to take the photo on the antenna.
Yeah.
So
It was a pretty epic
Engineering
one.
at its finest.
Engineering at its finest. We had Lexi up there kind of like, tick. There we go. So, there we go. Our project. So what our project was, it was to design and test a method to accurately count meteors using the materials that we had available. Now this, when we said accurately test, this meant decreasing all the interference that we had from local disturbances like electrical boxes, cars,
Spark plugs,
lightning storms.
even some lights. We had a lot of problems with really high intensity lights causing a lot of interference, which really looks like this, but
yeah, it looks what it basically is it jumps up whenever you get a lot of interference like that, or it'll create a spike, and it kind of makes our data hard to read because a meteor ends up looking like a spike also. Yeah. So these areas also include the sporadic E event like I was talking about earlier, and that right there is a picture that David took off of one of his screen caps of the sporadic E event happening. Yes, and another issue that we had is that lightning. There's a few storms during the time we were taking our experiment happening, and it ended up causing a very weird skew of data that we ended up just having to throw out.
So when we started this project, we wanted to come in and we wanted to observe the meteorites in data forms like this, and then we wanted to go out to Carter Lake or somewhere kind of obsolete, and we could visually see the meteors and count to make a reference point. You know, we measured 20 meteorites here, and we counted 15 in person. So that kind of got difficult really, really quick with clouds and storms and just the time of year we did this in. It got difficult to do that. So
yeah. So at the very end, our entire hypothesis and goal was to create an accurate way to read this data.
So we took it from more of a, let's see what the data is, to more of an engineering point of view.
So we decided to go for what is the best location for radio astronomy. So like we said, we initially started out here at the high school, and we got some very interesting findings. For example, whenever a car starts up, the spark plug ends up making a little frequency that we were able to detect. So whenever lunch would happen or something like that, you would get a whole bunch of meteorites that looks like the Earth was about to be destroyed. And so there's a lot of interference around the school due to the cars and due to large equipment starting up in the school, so we needed a better place to go. So I know some people at Shaw Farm, there's some relatives, and we found a relatively radio quiet place at the farm. So what we did is we set the telescope up there from August 3rd to August 20th in 2015 during the height of the Perseids meteor shower. This allowed us to detect the meteors, for one, that we knew that they were there because this was a shower that happens pretty consistently. And it just allowed us to basically run the experiment with relative ease and no interference.
And what was nice about it is we could set up an experiment for, I think we did 3 days at a time.
We did it. Well, the way we ran it is that we went there every 3 days or so and we stopped the recording, but the experiment ran 24/7 for this space.
So it's really, you set it up and you can go and do your thing, and then you can come back later and see all the data. So it was a really good way to, have a lot of data in a really little amount of time of setting up and doing the experiment.
Speaking of data, that's what the data looks like. I know, it's kind of like you look at it and you're like, what on earth does that mean? Who's dying in that picture? So what that basically is those spikes that JT is pointing at, those are meteors. So those are times when the signal is coming from Mexico, bouncing off that meteor, and the signal we're getting a sudden boop, right there. There's the signal, we see it. Now what we're able to do with this is we're able to go there and say like, okay, that's a relative meteor, that's just some static, that's over there. Visually we're able to see that. We got David Eckhart's experienced eye to help us with some of that. And we did this, and we created a program also that we set up that Dr. Terry Bullitt wrote. It was set up so that we can monitor certain thresholds. So we'd run it through the program, and every time that the program ran and detected a spike that was over a certain amount of time, but when it exceeded a certain height threshold, that it would mark that as a meteor count.
That was a lifesaver, to be honest, because we were running out of time and we had weeks of data we had to count and go through, and so that was a lifesaver.
Now with this, it did 45-minute intervals, so we were able to actually test our experiment off both the visual count and the program count. Results from that, however. So from moving from Berthoud High School over to the Shaw Farm, it decreased a ton of interference. It was night and day virtually. Now, what we also were able to do with this is that we did run into some interference while at Shaw Farm. A big thunderstorm did occur and stuff like that. We just had to throw out those days, naturally. And from that, we were able to test our programming.
So when we got to the farm, you know, we thought it was a great location. You know, a lot of diesels don't have a spark plug, so there's no interference with the diesel tractors. And so we were pumped up, and we're going to do this data, and then we got our data back, and we couldn't figure out what it was because there was a gap in our data. Everything has shifted up, and we really couldn't figure out what it was. You know, the lightning storm, yeah, we had some spikes, but it shouldn't have caused what happened. So we had to go back to the farm, and we had to look around and figure out what the problem was. And it actually turned out to be just a light. It was just hanging on a barn.
Giant light. It was a safety light that they kept so that no one would steal the tractors.
Yeah. So that kind of put a bump in the road.
It created a jump between whenever night would turn on, we'd see this giant lift in background noise, and whenever night would end, morning would come, it would just drop back down to normal. And we're like, what's going on here?
So what was nice about that is we could look at our data and said, okay, it starts at 6 o'clock and ends at 2 o'clock in the morning, so something's going on right then. So it wasn't really, you know, wherever. And
from all these little setbacks that we had, we were still able to calculate our meteor count for those days, and we were able to determine that the program that we writ for one detected about 23.25% more meteors than our visual count. Now this was because as we were looking around, even with an experienced eye, you have like, okay, if it's above this threshold, it's a meteor. If it's below this threshold, it's a meteor. Whereas a program will actually be able to follow that threshold a lot better. So if you're like, I'm not really entirely sure, I'm gonna throw that one out, I'm gonna keep it in, the program's able to go like, nope, that one is within the criteria, therefore it can be marked as meteor. That way you have a consistent basics.
So with more on the program, we had to test our program and make sure the program is actually accurate to work, really. So we had to take the visual data and we had to sit down and we had to take a piece of paper and, you know, here's our threshold. Anything above this is a meteor. Maybe we got to check, count, and then check the program. So it took a lot of time and a lot of our mentors' experience to say, you know, that's a spark plug. That's not, you know, a meteor or lightning bolt.
That's a lightning strike. That's just a smug on the chalkboard column.
Yeah.
There's a lot of things.
Yeah.
There you go.
So to end the project, we kind of went away from, you know, let's count meteors, because we wanted to see the curve of the meteor shower originally. And with all the problems we had, we just wanted to figure out a way to accurately count the meteors.
So through what we were able to test with moving to Shaw Farm, switching over to a dipole antenna, going over and looking at the program, running a program actually, and debugging that so it works properly, we were able to accurately decrease our entire meteor count. Now, our initial goal, unfortunately, this season was to do an optical to visual count ratio, saying, oh, hey, do we see more, do we hear more? Unfortunately, that's going to require further testing to do it. But now that since we have this set and tested way of detecting these meteors, we will be able to, with further research, clearly label any interference and any meteors that we are able to detect in the future.
Is there any questions?
Yes.
So, your detector worked 24 hours a day, I'm assuming, so you weren't able to collaborate with your visual.
Yeah, that's the reason why. The reason why we were having an issue with that is that we had to eventually drop the visual data for it, because with all the nights that it'd get cloudy and with all the nights that it'd get it, we wouldn't be able to see it. Whereas with a meteor, it can, with radio waves, it just goes straight through clouds. You can see it, it runs 24/7. So we decided it would just be better to have a tried and tested way to make sure that once we ran a few times, make sure we are getting it accurate with our dipole antenna, that we will be able to then make it more accurate using programs, quieter noise spaces, and other factors like that. All right, we'll hand you off to our secondary group. This is, and let them introduce themselves.
I'm gonna sit down.
Okay, so hi, I'm Zach. This is Xander and Sierra, and we did a slightly different route. Colin's going to explain something a little bit, that's why he's still up here. So our first thought after we kind of split off into groups was to just, instead of doing a local thing, we used the disk in Green Bank, West Virginia. And so we just, through this great website and program called Skynet Jr, you can schedule times to actually have the disk point at various parts of the sky to just measure whatever you want to look at. So we just used some time, pointed at various nebula and stuff, just looked at the results, seeing what we could find. And we eventually settled on mainly looking at Cassiopeia A, which is a supernova remnant, Rosette Nebula, and the Crab Nebula. And we discovered among them the results that it was different from everything else that we had looked at for the Cassiopeia A and Rosette Nebula. There was a double peak in the hydrogen line that we had. So that's the double peak there that we were seeing in our results, and Colin has a good explanation for those.
Okay, all right. So what we're seeing here is we're seeing a Doppler shift and a hydrogen line. So I'm going to go quickly through what these are. So what a Doppler shift is that if you ever hear a car go down a highway, or like one of those cool little Nerf whistle footballs that you throw and you hear the whistle go wee right by you, there's the waves that are coming at you. As the waves are coming at you, they're compounding together and becoming closer together. And as it's going away from you, they're pulling apart as the object is moving away. Same thing happens with sound, same thing happens with light. So as an object is moving away at light years a second, basically, well, not that fast, actually. Holy cow. At thousands of kilometers a second. Yes, that right there, we break physics if we do that. But, so if it's going away at thousands of kilometers a second, suddenly the light itself is actually being pulled apart slightly, and we were able to detect that as a redshift or blue shift. So a redshift is when the light is becoming longer, and a blue shift is when light is becoming compressed towards you. That is what you're seeing here. As the light is becoming compressed on this side, it is coming at you, and as it is becoming expanded on this side, it is going away from you, so it creates a double peak in the hydrogen line. Now the hydrogen line is a single one sort of bar of radiation that a hydrogen atom will get off. What happens there is that as the atom is spinning and running its natural course, after a couple million years, it basically gets bored, and it flips. And that right there, when it flips the charge, when it flips the rotation of the atom, a single wave of light, of radiation in this case, is jettisoned from the atom itself, and that happens to all hydrogen atoms within the entire known universe. So no matter what you're looking at, you can expect this hydrogen line to happen. And whether or not it's moving away or towards you, you can tell whether or not there's a Doppler shift. Thus, the universe will be expanding, contracting, the object is coming away from you, is running away from you. And basically you can discover whether or not the universe is expanding / if this object is expanding itself. And with that, I give you back to Xander.
1 second. Was that understandable to everyone? Does everyone have any questions? Okay, good. Go ahead. Here, I will. Yeah. I'll take this as well.
Okay. So after we found this double peak, we wanted to do some research and try to figure out, what it was, because we had no idea and the mentors hadn't really seen that before. And we went through a whole bunch of different sources. We just kind of Googled stuff, and then Jay to talk to some people that he knew at different universities or things, or different organizations. And we really couldn't find any information that kind of lined up exactly with what we found, which we thought was really interesting. And so it's not something that hasn't has never been seen, but there's not really any documented work about trying to figure out what it was, or like kind of the specific data behind it, or the calculations. So after that, because we couldn't really find any information and none of the mentors could, we just kind of brainstormed, during kind of some of our lunch sessions, what might be causing this. And as Colin kind of explained, we think it's because the actual object is expanding, because the velocities that we got from our equations later proved that it was expanding more than what they think the universe is expanding at. So we must be reading some other thing. So these are the two objects they were looking at. These are kind of the pretty photos from the space telescopes, using different X-rays, filters and stuff. So Rosette is on the side. That's the nebula, and Cassiopeia A is the supernova remnant. And so just by thinking about a supernova, that it's exploding, so it's expanding. And so our guess was that both of these clouds of gas are expanding from the center outward. We're not sure if they're a perfect sphere or even close. But we know that what we're seeing, we think in the double peak, is the front wave of that gas and then the back wave of that gas. And each of those would create a peak when it kind of gets to the densest part, the wave of that moving forward and away from us. And so this is, again, the data that we saw. This is the full output of what we got from Skynet Jr. So we did this a couple different times to look at our data, and it would change a little bit, but we ended up getting about the same data all the time, except for the polarity switching, which is the green versus the red line. But that's not something we were looking at. We were just looking at what the graph looked like. And so we would input our data for a certain amount of time, and for the telescope, the way we did it, it would just track the object. You can also do different things where it does patterns that kind of cross across the sky, and you can try to see a bigger area. But we knew what we were looking at, and we could plug that in and tell it where it was in the sky, and it just tracked that. And then we put in the rest of our parameters, and this is the graph that it outputted for us. And then all the data also comes out in an ASCII file, which is a kind of text file that just gives us the specific data points. And so we were able to look through those and figure out where the peaks actually were along the graph, because there's a lot more data points than you can tell in that graph. Each little point is like a cross, and
there's like 80,000 data points.
Yeah,
it's
so
ridiculous.
depending what you set it to, there would be more or less. So we had to look through and figure out where our graph started changing so we could find the peak. And then we use that data to plug into our equations, which is in the next slide here. And so we...
Do you want to point at stuff while he's
Oh, I
on?
have.
Oh,
Yeah.
okay. So,
Okay.
so we wanted to figure out velocity, which is the V there. And that goes in, the part that we plugged in was the frequency. Okay. So the observed frequency is there, and that was the difference between the two peaks. So that was along the x-axis, the horizontal one, the difference between those where the peaks would be, and then the hydrogen line would be in the middle of those, the equation that you would get, or the line. And then that is multiplied by the speed of light, which is c, over the normal frequency of the HI line, which is there on the bottom in the hertz. And so those are our two equations for the different objects. And once we went through all that, we were able to get out these two numbers, which compared to something here on Earth, that's going really fast. It's something like 30,000 miles per hour, I think. And then, of course, the lower one is a little bit less than that. But it's some crazy number. But if you look at some other data that we found using optical telescopes on the expansion of these two objects going outward, we were looking forward to back, and they were looking side to side because they were using an optical telescope. Our numbers are way less than theirs. And so they were getting about 4 million meters per second compared to our 50,000. But the main difference between ours and theirs is that they were very focused on their point, and we found out afterwards, you can see in the diagram on the side there, the gray part is the beam size of our radio telescope, and then those are the two objects we're looking at. And so we might not actually be getting the data just from those 2 points, because we're seeing so much around each of them. We're not really sure what we were seeing, and so we would have to get an instrument that would see a finer point in order to determine what actually we were seeing, and compare that to other data. And it could just be that for some reason the cloud is expanding side to side faster, and we do have correct numbers, but because there's such a huge difference, we're thinking that somewhere along the line our data got messed up, or we just are seeing more of space than we would like to. Yeah, and so we're not quite sure the actual answer would be. So.
Okay, let me take the pointer. Okay, so given the fact that there's not really any other research done on this, like the double peak, and that even though we found one source, as Xander was just saying about the velocities of these two, the supernova remnant and the Rosette Nebula, since they were so far off from ours, we didn't really have anything to compare to. So this was kind of at this point in the experiment, we were just seeing what we could do with the data and the results that we got, and just see if we can theorize and figure out a reason that it happened. Just going into our own research and not really basing it off of anyone else's, mainly because there's not any other research on this the way we did it. So again, those are the two velocities there at the top, and we've got that little chart down there showing the age of these two celestial objects. And so you can see that the Cassiopeia A supernova remnant is much younger than the Rosette Nebula, and that is because since it is still a supernova, it is still expanding at a much higher rate and velocity than the Rosette is, because of the fact that there's been so much more time that has passed since the initial explosion. And so just that comparison there of the age just shows why there's such a difference even in our two velocities between the Rosette and Cassiopeia A. So then we've also got the size of them, and Cassiopeia is much smaller, and so initially it is going to expand at a greater rate. And also if you have a smaller object, think about if a figure, an ice skater, a figure skater or whatever, they have their arms out and they're spinning, and then they bring their arms in and they move faster. Since the smaller object is, since Cassiopeia is the smaller object, it's going to spin at a faster rate and expand out faster than a larger one would. And that's why also the Rosette has a lower velocity. And then we've also got the distance from Earth down there just as another comparison. We were just trying to figure out if there's any correlation at all with those facts about the two celestial objects and why our results were what they were. And from this, we discerned that the age was the most influential thing in why we have such different velocities for these two. And given the fact that they both have the double peak, even though it's reversed, they still have the double peak in a lot of the other objects that we started looking at. And we also looked at Sagittarius in the beginning too, to see if any other objects have the double peak, and it was only these two. So just looking at the age of these helped us theorize that there is a possible correlation between the age of the supernova or the nebula and why there will be a double peak and what the velocities will be. So given that we didn't really have anything else to go off of, and the fact that this was more original research, and we don't know for sure, but if we had more time, we would go a little bit more in depth and see if there was anything else that could be another theory of why the galaxy, or not galaxy, the celestial objects behave the way they did, and why the velocities were what they were. This was just our main theory of right now, what we with the time that we had and the resources. Our main thing was just that the age of these two is what causes the difference in the velocities. Are there any questions on this? Any like detail or just overall? Yeah.
If I recall, did you have your double peak, that one was red shifted and one was blue shifted?
Yes.
Any thoughts on why they aren't both red shifted?
Like why they're opposite? Do you want to? I'm not. Okay.
Okay, so the reason why we're thinking, if I understand the question right, that there is a red shift and a blue shift and not just only a red shift or only a blue shift? If I'm understanding the question right, is that correct?
Maybe I misunderstood where you said that. I thought you said that the hydrogen line.
Oh yeah, so what it is that right here, basically almost right in the center of that, there is a hydrogen line that is occurring. The red shift and blue shift that we are detecting, we believe is from both sides of the nebula that is expanding. So the part that's moving away from you would have that Doppler shift that is then shifting it more towards the red because it's expanding the light waves.
My follow-up question was going to be, is the center of the hydrogen line, is that in between those two shifts?
It's not quite in between, depending various on the nebula and other parts, but that is mainly due to, for example, if there's a lot of hydrogen moving away from you, whereas there's just a little bit moving towards you, or if it's moving away from you faster than it's moving towards you, depending on the speeds, the shift will vary between where the hydrogen line is at. So, for example, the hydrogen line might be slightly more on the red shift side if the entire nebula is moving away, or if there's just more hydrogen moving away that way. Not hydrogen, I mean. If there's, basically if the entire nebula is moving away, then you'll see more of a red shift on there. The hydrogen line, however, will stay the same from what we see, if that makes sense. Okay, Xander can probably explain this better.
I was just going to add, so I think one of the other things you were kind of asking is why one peak is taller than the other. So we didn't really look much into that, but that could be, like Colin was saying, there was more mass on either side, but that wasn't a determining factor in the research that we were doing. We were just looking at where the peak was, the vertical line from that. And so there could be something else that we could research based on that, of why the one object has the higher peak on the other side, and why on Cassiopeia it's so much higher. And yeah, so that could be a whole other project that somebody could do next summer if they wanted to look more into that. So.
Giving you ideas for this year's junior STEM projects.
I'm taking notes.
Yes, and I.
Yeah.
Okay.
All right. Yeah.
So as I understand it, and some of the backstory here is that you guys had a little bit of a task convincing your mentors what you had was real data. Can you talk about that a little bit?
Yes. So let me
go for this.
And so one of the main things that we definitely noticed and we used to kind of help convince them was that we went back, so Skynet Jr. keeps all the logs that everyone does, and so we went back and looked at previous logs of the same stuff, of like Rosette and Cassiopeia.
As old as Skynet is.
And they didn't have the peak. It was a recent development. So we then did more research of if something came up with the disk, to see if there was an anomaly or something.
Change in program. We even went so far as to contact the people over there saying, hey, what's going on here? Is there a shift in the disk or something like that? And everything was A-okay as far as we can tell.
It was just a new development. It actually, I think the soonest that we could find evidence of it was at the beginning of the summer. So we found this about midsummer, and it didn't exist even in the spring.
Yeah. So that's...
Yeah.
Is it
so.
Changing? Or are you not continuing?
As far as we can tell, it's not changing right now.
Yeah.
As last I checked.
Yeah. So I think we retested it maybe in October or something, and it was a very similar. So a couple months ago, and it was a pretty similar graph. And the reason that it may be different than other people's data was that they could have put in different parameters. It doesn't tell you a lot of the parameters that they put in unless you go through the ASCII file, and it gives you somewhat more data about all their specific inputs into the program. And we were kind of using a little bit more upgraded program, I think, on the software side. So something could have changed there. And so it could have just been the difference between our inputs and how we actually ran the tracking versus, if they were running a different pattern or something. So.
Do you know about how many times bigger is Rosette than Cassiopeia?
So
I
I think,
think on the chart.
yeah,
The chart or that?
no, that one,
Yeah.
yeah.
So it's
So-
10 to 130 to 10.
Yeah, so it's about 13 times bigger. And that's just kind of a rough estimate, we don't know exactly. But, yeah, so.
That's rough estimate there.
Given what you guys know now, would you give up another summer doing this kind of research?
Possibly.
I'm going to push a group of juniors to actually just continue this.
Yes.
And
By push, we mean slightly maybe
tell them they have
blackmail.
no choice.
Yes.
Are you talking pure pressure?
No,
we're
we're
talking much
talking about
severe.
seniority.
Yeah, seniority.
Sound like
Yes. There you go. Any more?
Did you inquire with the NARO whether or not they'd be willing to, look at it with a different telescope, a smaller beam width? I'm sure the answer is no, because you didn't include that in your presentation. But do you know what the beam width is in some of their larger telescopes?
Yeah, so we didn't ask specifically about using another one of their telescopes because this was the only one that they have set up for the remote access. And a lot of, I think the other ones are kind of reserved more for the people, the universities or, people that are a little bit higher, in knowledge or, schooling than we are. But we did ask them if there was a way that they could implement the telescope we were using to have a smaller beam width, because there's a slot to change it in the program, but it doesn't allow you to. So we were wondering why that is a set point and if there was a way that they could change that or if that's just a function of the dish and it has to be at that set beam width. And pretty much the answer they gave us was they weren't totally sure, at least the people that we were asked, but they were going to try to look into that and see if maybe they could change it. So maybe next summer when the juniors do it, they could get a little bit better data from that. So.
We're pretty sure the engineers are currently still bickering about that right now.
Yeah.
They've been yelling at each other for a while.
Yeah. So.
There you go.
Yeah.
Well, because of this gigantic discrepancy, I was kind of curious about where did your equation that you used to determine the velocity, where did that come from? Is that a standard? I know nothing about it.
Do you want to take that, Sierra?
Yeah.
Take that, Sierra? Well, so, do you want to?
No, you're good.
So we originally started out with an equation that was similar that we got from Mr. Kindt from one of our physics textbooks, and then we found another one online that was slightly different from that, and then Mr. Bullitt gave us this one, which we ended up going with because it was the most simplified version for showing other people, and all of them I think were kind of just simplifications or variations of the same equation, and so it's just a general velocity equation, and we looked between the three, we figured out, what specific points we needed to input, where the, the speed of light needed to go. But it is just a general physics equation. It's not really anything special for radio astronomy.
So it's possible, we did dig through the ASCII data to get the points that we used in those equations. It's possible that the data wasn't completely accurate, that we were pulling from the wrong spot. Those could explain some of the discrepancies.
But we think we pulled the right data from those ASCII files, but there always could be human error. So.
How many times did you repeat the measurement to verify your?
That's the
many times.
So,
I don't even remember
I
many to count.
I recall it probably took at least 10 to convince David alone that was in fact a thing.
So, yeah, I know that Sierra ran her own with some set parameters, and I ran mine, and then when we looked at them both, and then ran more when we are as a group, and then we did those other checking ones, kind of near the end of our project to make sure that it was still the same thing. So I'd say maybe at least 15 times, probably. So somewhere around there, and those weren't. We didn't do the same thing every time. So there was probably at least 3 of the same thing. So changing the variables.
Yeah.
Are
there other target objects that you might be able to try for your next students?
Just go ahead.
So there are other objects that are out there that we can detect with this telescope that might have the shift. These are the main ones that we were noticing and seeing if there was any sort of correlation between how they formed and how the nebula is actually detecting the shift within it. That might be just something that they look into, being like, oh, here's our two nebulas right here. Let's find a couple more like it and see if it still occurs within it. And then, for all we know, there could be many. This could be a common occurrence that we just have detected right now.
Yeah, and one of the things at the beginning, Sierra mentioned that we looked at Sagittarius. We're just scanning various objects in the sky, like, let's look at this and see if we can measure data from it. And then we stumbled across these. So we did check others as well, and it is possible that other similarities exist.
Yeah, and no, Skynet also gets mad when you point at the sun.
Well, you are allowed to do it with the radio telescope, though, because it won't damage it, but all the optical telescopes give you a warning. So.
Who was that?
So.
Are you looking into publishing a paper, and at this point, is there any talk about a Nobel Prize? Or?
A lot of talk about Nobel Prize. It's the only thing talked about in science nowadays.
Yeah. So we actually have our paper that we had to submit for the STEM project, and we were going to look at that and rewrite it and reorganize it, and hopefully submit that to one of the online magazines.
Yeah.
Oh, right.
I'm going to mess up the name. Someone correct me. The Jove Bulletin or something like that?
Radio Jove Times.
Yeah.
Whatever they call it.
It was a newsletter.
There's a newsletter put off on www.radiojove.nasa.com.
And it mentioned us. It had that picture you guys saw of us.
Yeah. And so we got published on that website as a newsletter sort of thing.
Yeah, so I'm just explaining that really quick. So the Radio Jove is the receiver that we used, the one that we added on and used later. That wasn't that Yasu ham radio that you saw, and that's something that was developed by NASA for hobbyists to use so that they could detect, these radio objects without having to, design their whole electrical system or find all these different parts. It was a simpler version. So yeah.
Can I speak out of turn?
Go ahead.
I'm one of the mentors, but you hit a very soft button in my heart. They could present this, Jay, it's March in Prescott, but we're lacking transportation, we're lacking a place to put them, we're lacking a way to get them there and back. I want to see them present. Yeah. If anybody wants to help out, please.
What are the dates again?
Yeah.
It's mid-March.
Is it on the sheet?
It's March something.
It's not on there.
Is it 11, 12, 13 thing?
Yeah.
March 11, 12, 13.
So
Pending investigation.
To be clear, what do you need? Money, transportation, what are you asking for?
I think all of the above.
There's a conference there that we were invited to.
Radio Astronomy, Jay, conference.
Yeah.
And yeah, they deserve to present. Thank you.
Yeah.
But
So-
we need to get them there and back.
Yeah.
Yeah.
So what's the reaction been to the publishing on the website and everything? You guys got any reaction from people reading it there?
Not very.
It is read. I
Yeah.
got feedback.
Yeah,
Yeah.
he's on it.
Read a number of times. People have looked at it and they're scratching their heads too.
Cool.
So
Yeah.
we're on that.
Yeah,
Yeah.
so and we did, we all thought that was pretty cool that, we just, kind of got put into this over the summer and we had
And
no
then
idea what we were
stumbled across
doing.
it.
And then we were able to, kind of be put into this community and have people actually look at what we did, so.
I really kind of just bumbled across a celestial object in space and was like, hey, we're here.
Yeah.
I have a question, maybe not a very fair question for Mr. Kindt. How would you score this anniversary?
No. shift that over to Domenico, because Domenico was the person grading this.
So I'm hearing like 104%, correct?
I believe that from the STEM class, we all have 99.2 somethings, so.
Something like that.
That's the right answer.
Yeah.
And the ones that was in their paper, and they're modifying them.
Yeah, that was, so, yeah. Fine.
Yes?
Well, Zach's heard me say this, but there's a quote by Isaac Asimov, the author and scientist, that most of the great discoveries in the world of science has not been, and I'm paraphrasing, has not been met with a eureka, I found it, but what the heck is that? Yes.
That's pretty much exactly what we said when we found this.
Like what?
So. Yep.
Actually, I think the first thing that was said was, great, we broke it.
Yeah, we didn't think we had anything special at first, and then we were like, oh, maybe we didn't break it. So.
Who knows?
Did you have a question?
Yeah. You guys have just done a great job presenting, and I'm sure you guys are going to go far. I was also curious if the other mentors and leaders wanted to say a few words about what you learned or what you enjoyed.
Silence.
Thank you for putting that
Another star.
Well, I would like to say that I think this is, both projects have evolved along what I would consider to be a very typical path for a scientific project. As a practicing scientist myself, the engineering problems that you came across with the meteor studies are classic, and the fact that you stumbled upon something without wanting to, looking for it specifically, is also very classic. I think most great discoverers are that way. You hardly ever find something new by intention looking for it. And so I think in that case, it's very professional how this came out, and how they worked. I was very proud of all of them, and it's actually a real pleasure to work with them. It's actually been the highlight of my summer for Wednesday, so we can get together both with the students and with my other mentors, and we could exchange ideas ourselves, because we got to know each other better and learn much from each other as well. And I also learned a lot from the students as well about how to teach. I'm not a teacher.
Well, thank you all very much. Well, I think on behalf of LTO, and I'm guessing everybody here, I want to congratulate all of you. I'm really sorry that one of the students was not able to be here tonight. Lexia Wise had another commitment, couldn't be here. But she was an integral part of this project. It's really been a pleasure working with you. And while in the presentation, as all good scientists, they sort of downplayed the significance of what they did, I can't overemphasize the importance of this last experiment, because when we shared this information with the National Radio Astronomy Observatory in Green Bank, the people who own this 20-meter dish, they simply couldn't believe it. Just like Terry, David, and I, what did you do wrong? And that literally was the question back to us. This has laid the groundwork for some very, very serious graduate study over the next several years. The original discovery came with this group right here. All of us are still trying to figure out what does it mean, what do you make of it. But isn't that the excitement of science? And that makes it worthwhile. I want to thank all of you for being here tonight. Michael, what's the sky prediction?
The sky is kind of iffy, the clouds move back in, so we can look at the moon. There's maybe one or two bright stars that are visible. Orion is not visible, the Orion Nebula is not visible right now. So if people want to go see the moon, we have this telescope running. And feel free to go up to the dome and take a look at it. Bring a coat, it's very cold up there. But for the rest, there's not much to see.
Okay. thanks again. Congratulations.